Hi. In this video, we'll talk about the relationship between the graph of a function and the graph of the derivative of the function. Now, what I want to do is look at certain cases, and then we'll lead up to an example from the textbook. Now, for this first example let's say if the graph of our function is this straight horizontal line. In this case, it's the function y equals to 4, or f of x equals to 4. Now remember, the derivative gives the slope of the tangent line at a point. So any point on this line, if we were to find the tangent line, it would still just be a horizontal line, right? Now, what is the slope of a horizontal line? Now, if you remember, the slope of a horizontal line is 0. So therefore, for every single point on this line, the slope of the tangent line would be 0. So that's why the graph of the derivative would look like this in blue. It would be the horizontal line that y equals to 0, because every single point on the derivative would be 0, because again the slope of the tangent line for every single point would be 0. So that's the first special case. Now what if we have another line, but it's not a horizontal line? But now for this function, which is the y equal to x plus 2, again if we take any point on the line and take the tangent line, then they all would have the same line, right? And now this, again, the derivative gives you the slope of that tangent line. So in this case, well, let's see, our tangent lines are all going upwards. So we have a positive slope. And in this case, they all also have the same value, right? Because every single tangent line is actually the same, so they all have the same slope. So in this case, the graph of this one would be the line y equals to 1, because it's growing at a constant rate. So in this case, it's at y equals to 1 is the derivative of the function. So this would be the graph of the derivative of this line. But now what if we had a line, but it was going downwards and a little more steep? Well, since it's going downwards, the slope of every single tangent line would be negative, and also since it's more steep, then it'll be a larger but negative value. So in this case, that would be y equals to negative 2. Now if it was even steeper, then it would be, again, y equal to, let's say, negative 4, negative 5. It would just be a larger negative value. But again, it's the same value for every single point on the derivative. Now, that's dealing with straight lines. But what if we had this parabola? Well, let's look at this parabola first, and let's look at some of the tangent lines. Let's say first, what about at negative 3? What would be the graph of the tangent line for that point? Well, so we'd have this point here in purple. This would be the tangent line at negative 3. So we know that the tangent line is going down, so we have a negative value, and it's pretty steep, so it'll be a pretty large but negative value. In this case, it would be negative 4. Now if we look at another tangent line, let's say at negative 2, then it's still going downward, so the slope is still negative, but it's not as steep anymore, is it? So the tangent, or the derivative for the function at negative 2, it will be negative, but like I said, it won't be as large of a negative value, and actually it'll actually be negative 2. Now what about at negative 1? If you notice, that's where this one turns from going down to start going up. That the tangent line in that case would be this horizontal line. So if you remember, the slope of a horizontal line is 0. So the derivative at negative 1 will actually be 0. And then looking at, let's say, what about when x is 1? So that'll be this tangent line. Oh, actually, sorry, 0. I skipped 0. So first, let's say about 0. When x was 0, again, it's a positive slope for that tangent line. So it'll be positive for the derivative at 0. And then if we kept going along, when x is -1, it's going up, so it'll be positive, but it's going up even quicker, so it'll be a larger positive value. And when it's x is 2, then it's an even larger or greater positive value. So for that one, it's again, you can see it's a really steep line. So the slope of the tangent line in that case is actually 6. So the graph of the derivative for this one is actually this line here. Now let's make sure we all understand it. So it's going down as we're going from left to right. But if you notice, the tangent lines will get not as steep as we're going along. So it'll be negative values, but they won't be as large of a negative value. So it'll start getting closer and closer to 0. And when we have this turning point, that's when the derivative is actually equal to 0. And then from then on, we notice the slopes are positive for the tangent lines. And actually, the more farther along we get, the steeper the lines get. That's why there'll be even larger positive values. So this will be the slope of the tangent line for this function. Or sorry, that'll be the graph of the derivative for that function. Now let's kind of think about the same way for this one. So it's going down here, so it'll be negative. So the derivative will be negative, so it'll be down here. And at this turning point here, that's where the derivative is 0. So that tells us the graph of the derivative will hit the x-axis at this point. Then it'll be positive, so it's going up. But if you notice, it gets steeper and steeper, but then it starts slowing down. So what will happen is it'll be positive, but then it'll start going down because it'll be slowing down. And at this point here, this is again one of those turning points. So you see that the derivative will be 0 at this point. So it'll come back to the x-axis. And then you notice the tangent lines will be going downward, so it'll be negative. But once again, it'll get steep, but then it'll start being not so steep. So it won't be as negative. So it'll go down, then start coming back up. And then once again, at this turning point, the derivative will be 0. And then from then on, it looks like it's just increasing, so it'll get larger and larger positive values. So if we graph the derivative for that one, it would look like that. So like we said, it's negative here because it's decreasing, it's going down. And at this point, this turning point, that's where the derivative was 0. So like we said, it was going up and getting at a steeper, but then it stops being as steep. So it's the graph of the derivative starts going down, and it hits the x-axis here because, again, that's one of these turning points. And then it's decreasing, has this turning point here. So once again, that's where the derivative would be 0. And then from then on, it's just positive because it's going upwards. Now what about here? If you notice, this is just a special case that we have one of these ones where at this point here, the derivative would be 0 because if we graph the tangent line, it'll be a horizontal line. But if you notice that it is increasing here, so that means the slope of our tangent lines are positive, but then it's still increasing. So what means it's the derivative's positive, and then it starts slowing down, but then it gets positive again. So that's why the graph of the derivative for this one will look like this. Again, the derivative is positive because it's going up. It's 0 at this point because we have the slope of the tangent line would be, the tangent line would be a horizontal line, so the slope would be 0. But then it starts going up again, so again, it'll still stay above the x-axis, which means again that it's a positive derivative value. Now one special case before we look at the example from the textbook, and that was the absolute value function. Now if you remember from the textbook, it does say that the function is actually not differentiable at 0 because it has one of these sharp corners, because as we're approaching from the left-hand side, it is a straight line. So if you remember from that previous example, it's a straight line, but it's going downward, so it'll have a negative slope, but it'll also be a constant negative slope for all the way to here. But then it takes this sharp turn, and for all of these values here, it has a positive slope, and it is a positive constant for all of those. So when we graph those, so for the left side of 0, the graph of that would be this horizontal line, which has this constant value the entire time, but it's negative because, again, it is decreasing. But then it jumps to increasing at a constant rate. So that's why the graph of that would be, again, this horizontal line, because it is increasing at a constant rate the entire time from then on. So that's how you graph one of these. So if you see when it's non-differentiable, we have that the graph of the derivative is discontinuous. We have one of these jump discontinuities at this point. Now for this example from the textbook, they want you to, they give you this function and they want you to sketch the derivative. Now when I do these types of problems, what I first look at is where are these turning points that we had from those previous examples, like here, and this one here, this one there, that one there. Because if you notice, at this turning point, we know the derivative is going to be 0. At this turning point, the derivative again is going to be 0. At this turning point, again, the derivative will be 0. So that means that those are x-intercepts of the graph of the derivative function. Or if it has one of these ones where it doesn't, it's not a turning point, but it does have a tangent line which has a 0 slope. So again, it will touch the x-axis at those points. So for this one, if I were doing this, I'll see, okay, here my derivative should be 0. So I've got plot x-intercept there. And here also I know the derivative will be 0. So I'll plot another x-intercept there. And then I'll think, okay, it's going down, so that means it's negative. So that means my derivative should be, the graph of the derivative should be below the x-axis. And then after that, it is positive, and it starts getting steep, but then it starts slowing down, and then I'll hit 0 again. So I know it's going to go up, but then back down here. And then it's just decreasing from then on, so that just means the derivative will be negative from then on. So that's why they're saying, yeah, that it's negative, and then it's 0 at this point, and it's positive, and then it's 0 again at this turning point, and then it's just negative from then on. So I hope that helps with graphing a function, the derivative of a function, when you know the graph of the original function. Again, it doesn't have to be exact, but just to show, again, you know, okay, where is the derivative going to be 0? Where is it above the x-axis? Where is it below the x-axis?